Hey everyone, welcome back to AP Precalc. This is lesson 3.12. Let's get right into it. All right, so start with 3-peat F for today. Just remember there is going to be a Desmos quiz next class, so make sure you know how to do all the 3-peats from 3-peat E and 3-F, the two Desmos sections, because 3 of those questions will be reseen on the Desmos quiz next class. So just be prepared for that. Also bring your laptops fully charged as well. All right, so for the first one here, this is pretty similar to a 3-peat last class, but we have two functions, f and h, where f is this polynomial and h is this rational function here. And then we want to find the zero of j, where j is literally just going to be a composition of h of x minus f of x. This is what it should look like in Desmos, where I would literally enter the equations in row 1, 2, and 3 as f of x, h of x, and j of x verbatim. So even including the f of x equals part, the h of x equals that rational function, and then j of x is h of x minus f of x. And then just really remember you're looking at j of x. That's what we're asked about. And we want to find the 0, which is where it hits the x-intercept. That's going to be this point right there. I clicked on it and highlighted it so that we can see it a little bit clearer. This is going to be, our answer should be x equals 0.992, making option choice D the correct answer for number 1 there. If you need to, like I said, hide these two equations, just click on those two colors right there, and that will make them disappear visually from the graph, so you can only focus on the correct equation. All right, number 2, a geometric sequence has the form g of n equals g of k times r to the power of n minus k. We're shown a graph of this. What is the value of g of 5? So here we are looking for g of 5, and we can use either one of these two terms. Let's use g of 1, which we know is 16, and this is going to be our g of k. G of 5 will be set as our g of n, and then we want to find our common ratio, but we can kind of figure that out with this. Remember, we start at 16, and then our next term in the sequence is 4. Our common ratio is what do you multiply 16 by to get 4. In this case, you don't really need to figure it out or solve it by hand, when we can just think about it logically and know that our common ratio is going to be 1/4. So plugging in everything we know, we can set g of 5 equal to g of 1, which is 16, times 1/4 to the power of 5 minus 1. In a calculator, it should look like this, where I typed in the same equation, but I did f of x, so f of x equals, and then 16 times our common ratio of 1/4 to the power of x minus 1, because this was g of 1 here. So that's where that 1 comes from, that small subscript. Once we have that, we want to find the fifth term, so you just plug 5 in for x to get 0.0625. And so B should be the correct answer here, 0.063. That's that rounded. And that should be our answer for number 2. All right, number 3, which of the following statements is true about this function on the interval from 0.8 to 3? And we want to see whether the function itself is increasing or decreasing, and whether the rate of change is increasing or decreasing. These two are very different, so make sure you answer each one separately, kind of, and then find the correct answer. So here, what I would do is I would just graph that function like so, and then look at the interval that we're looking at, which is from 0.8 to 3. That's going to be this portion of the graph, which is really a decreasing graph, right? So the function itself is decreasing because it's going down. And so here, k should be decreasing. So we can eliminate a and b just from that. And then this is also concave down, right? Because it's a downwards U shape. So the rate of change should also be decreasing. That means any concave down graph as well. So D should be the correct answer for number 3 there. So today we're going to be basically talking about simplifying trig expressions. into a single trig function. So for example, I would give you a bunch of trig functions and say rewrite all of this in terms of cosine, or rewrite this in terms of sine and no other trig function. And that's what we're going to learn how to do today, is just simplify or write equivalent representations of trig functions or expressions. To do this, we're going to need to use a few identities to be able to convert from one trig function to another. So let's review the ones that I would expect you to know right now. These are our trig identities. The first one we have is our reciprocal identities. You need to know that sine and cosecant are reciprocals of one another, but remember opposite letters go together. Same thing with cosine and secant. So cosine and secant have opposite letters. Those are reciprocals of one another. Same thing with tangent and cotangent. So these, yeah, they have opposite letters, but they're pretty easy to match up. You know, obviously tangent and cotangent are going to go together. And then just remember, if tangent is sine over cosine, right, as a trig identity, then you know cotangent is going to be the reciprocal of this, which is cosine over sine. Right? These are the 8 that I would expect you to know, but a lot of this is from last class and the classes before that. So I'm going to give you a jumble mess of different expressions and identities, and I will ask you to rewrite it in terms of a single trig function typically. Let's use sine of x as an example here. These are things that it's okay to have as your final answer. You could just have sine of x by itself. You could have a number multiplied, so maybe 3 sine x, that would be okay. You could have 1 over that number, like 1 over sine of x. You could also have a number added or subtracted, so maybe sine of x plus 3, that would also be okay. And you can have sine of x to a power, maybe sine cubed x as your final answer. All of these are okay to have as your final answer. But when I ask for a single trig function in terms of only sine and no other trig function, I cannot see cosine or tangent or cotangent or even secant or cosecant in your answer at all. I also would expect this to be simplified to just sine x. So I don't want to even see cosecant in your answer. And basically, if your answer includes any other trig function besides sine, it's going to be wrong. And this is only for questions that ask for it to be simplified in terms of sine. The question will always ask what it wants to be simplified into, so just pay attention to that. So let's try example 1. Let f of x equal sine of x times secant x. Rewrite this as a single expression using tangent and no other trig function. So here, this is what we're looking for. We are targeting tangent. Now here are the steps. This is a very simple example. So step 1, split everything into its own fraction. So I'm going to rewrite this as sine of x times secant x. Then get everything in terms of sine or cosine. So I'm going to rewrite this as sine of x is already in terms of sine. I'm just going to put it over 1 as well because I want to put these in fractions. And secant is the reciprocal of cosine. So I'm going to rewrite that as 1 over cosine x. Then we want to cancel appropriately here. We don't see anything that you can really cancel. And then 4, convert into your given trig identity. So here, this is sine of x over cosine x. We can't leave our answer like that. We want to rewrite it involving tangent. Sine over cosine is just a single tangent. So tangent x is going to be our answer here. And that will give us full points for that question there. That's a really basic example. They will get a little harder, but it's kind of fun because it's kind of like a puzzle where you're trying to figure out what do I need to rearrange to get tangent of x as our final answer, basically. So here, let's try example 2. Pause the video now and try this one on your own because I'm about to go over the answer. So here, first, split everything into its own fraction. So I'm going to rewrite this as 1 over sine of x times tangent x over 1. Then rewrite everything in terms of sine or cosine. So this is 1 over sine of x times sine of x over cosine x. and then simplify when you can. We can cancel out a sine x. So we have 1 over cosine x, and then we are asked for it in terms of cosine. So that's just going to be our answer there for example 2. When you work through these questions, not just on my quiz, but on the AP exam, you will be expected to show this work, even if it's very simple. So show every step possible, because you actually will get no points if you don't show any work at all. All right, example number 3. Here we want to write this as an expression involving tangent. So first split everything into its own fraction. So sine of x over 1 times secant squared x over 1 times 1 over cosecant x. Now I'm going to rewrite everything in terms of sine and cosine. So sine of x over 1 times 1 over cosine squared x times 1 over cosecant is sine of x over 1. Here, simplify it, we get sine squared x over cosine squared x. So we can't cancel, but we can simplify a little bit and clean that up. And then this is just going to be tangent squared x, because it's 2 sines over 2 cosines. So tangent squared x should be our answer for example 3. Let's try example 4. Here we have cosecant x over 1 times tangent x over 1. Rewrite this involving secant. So first get it in terms of sine and cosine. So 1 over sine x times sine x over cosine x. Those will cancel out. We're left with 1 over cosine x, which is just secant x. So that should be our answer there. So getting everything in terms of sine and cosine makes it really easy then to convert to whatever trig identity or trig function that the question is asking for. Now, one other tool that we're going to need to use is what we call our Pythagorean identities. This is probably the most important equation that you will come across in this course, in the pre-calc course, just because it relates most of trigonometry together, and you kind of already know it. So think about this. Remember, if you have from geometry a right triangle with SOHCAHTOA with side lengths of A, B, and then a hypotenuse of C, what equation relates these two together, or these three sides together? It's the Pythagorean theorem, which is a squared plus b squared equals c squared. We're going to do that, but now look at it in terms of the unit circle. So if we have the unit circle here, let me extract that triangle, right? We have a right angle, you have x, you have y, and you have your radius, which is 1, and that is also going to be our hypotenuse. We also know that our x-coordinate is cosine theta, and our y-coordinate is sine theta. So in terms of sine and cosine, let's write this Pythagorean theorem in terms of sine, cosine, and 1. This is going to be cosine squared theta plus sine squared theta equals 1 squared. And we can honestly simplify this. I'm just going to switch this order. It doesn't matter. Sine squared theta plus cosine squared theta equals, and then 1 squared is just going to be 1. So you don't have to write the squared part. This is what we call the Pythagorean identity. So this is very, very, very important to remember. You will need to commit this one equation to memory. There's 2 more, but you will be able to just derive it from this equation. And I'm going to show you how now, but for now, just remember to commit this to memory. Because once you have that equation committed to memory, we can get 2 more equations for basically the price of 1. You get 3 for the price of 1. And the way we do it is we're going to take this whole equation and divide it by sine squared x to get an equivalent equation, and then take this one and divide it by cosine squared x. What that means here is we're going to take this and take each term and divide it by sine squared x, divide by sine squared x, divide 1 by sine squared x. And here, as a resulting equation, sine over sine is just going to be 1, plus cosine over sine is cotangent, and remember it should be squared, equals 1 over sine, which is cosecant squared x. So that is the second Pythagorean identity that you will need to be able to derive. I wouldn't even say try to memorize it because you can easily mix up a plus or a minus, but if you just know to take sine squared plus cosine squared equals 1 and divide everything by sine squared to get this, it's pretty easy to do. Now, taking the second equation and dividing everything by cosine squared, we're going to get sine squared over cosine squared x, this over cosine squared x, and then 1 over cosine squared x. To get sine over cosine is tangent squared x, cosine over cosine is 1, and then 1 over cosine is secant squared x. This is equation number 3. And so these two you basically get for free. Just remember to divide by sine and then divide by cosine squared and sine squared as well. Right, we will be using these three equations to also simplify some trig identities. So let's do that now. The function f is given by tangent over cosecant. Rewrite this in terms of cosine and no other trig function. So here, first split everything into its own fraction. So tangent x over 1 times 1 over cosecant x. And then put everything in terms of sine and cosine. So this is going to be sine x over cosine x times 1 over cosecant is sine x over 1. And we're wanting it only in terms of cosine. So let's simplify what we can first. To get sine of x times sine of x is sine squared x over cosine x. And now here, I see, oh, well, I have sine and I have cosine, but there's no trig identity that relates sine and cosine. But here's the key. Whenever you see a trig function squared, that's probably going to be a key to use the Pythagorean identity, more than likely. Not all the time, but more than likely. So if we actually take this equation and we rearrange it to solve for sine of x, so I'm going to subtract cosine squared theta from both sides to get sine squared theta or sine squared x equals 1 minus cosine squared x. I'm going to sub in this for sine squared x here to get 1 minus cosine squared, and I'm going to put x, not theta here, because that's what this equation is in terms of, over cosine x. And this should just be our answer for example number 5. This is a perfect fraction. It doesn't involve any other trig functions, and so this would be an acceptable answer here. All right, number 6. Here we have f is given by this whole mess. We want it in terms of cosine. So let's look at our trig identities, right? Remember, sine squared plus cosine squared equals 1. Dividing that, we also get 1 plus cotangent squared equals cosecant squared. And then we also have tangent squared plus 1 equals secant squared. So let's take a look at maybe how we can simplify these. Let's write each parentheses as its own fraction. We have secant squared x minus 1 times cosine squared x times 1 over 1 plus cotangent squared x. 1 plus cotangent squared x is cosecant squared x. So I'm just going to rewrite that as well now. And then we know secant squared x minus 1, that's probably going to be a key to use this third equation, which if we rewrite this, tangent squared x equals secant squared x. And then if you subtract 1 from both sides, that gets what we're looking to kind of replace. So this is tangent squared x times cosine squared x. And now putting everything in terms of sine and cosine, we get sine squared x over cosine squared x times cosine squared x times, this would be sine squared x over 1 using the reciprocal identities. Here we can cancel those out and we are left with sine squared x, and there's 2 of those. But we want to write it in terms of cosine. And so we can actually rearrange our first equation to get sine squared x equals 1 minus, and then we're going to subtract cosine squared x from both sides. So this should be 1 minus cosine squared x, and then this whole thing is squared because the sine x or sine squared x was also squared. This is going to be our answer right here. We can leave it like that. You don't need to FOIL it out because that answers our question there. All right, number 7. Rewrite this in terms of a fraction involving tangent and no other trig function. We have 1 minus sine squared x, and this whole thing is squared. I'm going to put that as its own fraction. We have secant squared x, and then we have, 1 over sine squared x as well. Once we have this, I'm going to replace, we know 1 minus sine squared x is, remember, sine squared plus cosine squared equals 1. So to see 1 minus sine squared, you get cosine squared equals 1 minus sine squared. So this is going to be cosine squared x, and this whole thing is squared, times 1 over cosine squared x times 1 over sine squared x. Here we can cancel out 1 cosine squared x with that and then that power to just give us cosine squared x over sine squared x. And we want this in terms of tangent. So this is actually cotangent squared x is what that simplifies to. So to rewrite it in terms of tangent, I'm going to put this as 1 over tangent squared x. So that should be our answer for example number 7 there. Example number 8. This was actually the exact same question from last year's AP exam. Out of 100 possible percent, only 28% of students got this one right. So if you're watching the video for the first time, pause the video now because I'm about to go over the answer, but I want you to try it first. All right, so solving this equation, I first see if we separate everything into its own function, we just see a 6 at top, or on top. We can just leave that as 6 over 1. Don't forget about that, though. Times 1 over cosecant squared x minus 1 times 1 over tan x. And then we want to write this in terms of tangent and no other trig function. So I see cosecant squared x minus 1. Once I have all my trig identities written down on my AP exam, you can just use that to kind of reference. But cosecant squared and 1, I'm going to look at the equation 1 plus cotangent squared x equals cosecant squared x. And then I'm going to subtract 1 from both sides to get cotangent squared x equals cosecant squared x minus 1. And then I'm going to replace this with cotangent. So this should be 6 over 1 times 1 over cotangent squared x times 1 over tan x. Here, if you want, you can cancel out a cotangent and a tangent. However, we could just also keep it simple. Do 6 over 1 times 1 over cotangent is going to just be tangent squared times 1 over tangent. And then if you wanted to, you could convert it to sine or cosine. You don't need to in this case. You could just cancel that out right there. But doing so, right, let's just do it like we've always been doing it. Sine squared over cosine squared times 1 over tangent, which is cosine over sine. Here, a cosine and a cosine squared will cancel out. So those just drop by a power of 1 to get 6 over 1 times sine of x over cosine x, which is 6 tangent x. That should be our answer. And so that was the correct answer on the AP exam. You did not need to go through all this. Honestly, as long as you showed that work and then you showed that you canceled out a tangent and a cotangent, you would then have 6 over cotangent x, which is 6 tan x. That would be enough work to get full credit for this question. All right, number 9. This one is a tricky one, so pause the video now, try this one on your own. Here we have, I'm going to write down all 3 Pythagorean identities now, just so we can work with them. Sine squared plus cosine squared equals 1. We have 1 plus cotangent squared equals cosecant squared. And then we also have tangent squared plus 1 equals secant squared. So taking a look here, I see 3 times 1 minus cosine squared over 1 times 1 plus tangent squared over 1 times 1 over secant squared minus 1 times 1 over sine squared. This is a lot. You won't see anything this hard, I hope, on the AP exam. 1 minus cosine squared, rearranging this formula, is going to give us, uh, here we have sine squared x equals 1 minus cosine squared x. So this is 3 times sine squared x. 1 plus tangent squared is just secant squared. So secant squared x over 1. And then 1 over secant squared x minus 1 is tangent squared x. Whoops, this is wrong. This should be, tangent squared x should be in the denominator. So doing that, we have 1 over tangent squared x and then 1 over sine squared x. That's just going to be kind of left as is. Here, we can honestly cancel these out right away. There's no use for us to deal with that, so let's do that, make it a little easier. And then this would be 3 times 1 over cosine squared x times 1 over tangent is cosine squared x over sine squared x, and then the cosines will cancel out. We are left with 3 over sine squared x, and that should just be our answer. You do not want to convert this to 3 cosecant squared x. That would be wrong because we only want sine there. So that's the end of the lesson, but I'm going to do something I don't usually do. And because this homework is a little tricky, not all of these problems, but some of them are a little tricky, I'm actually going to go over the first 12 questions on your homework. What I would really recommend, though, to do well on the AP exam as well as my quiz is you will get nothing out of this if you just go to this video for all the answers. Instead, what I would recommend is you try all 12 problems first, see what you can get, and then use this video to kind of check your work and or help you fill in any gaps for any questions you had trouble on. All right, so let's work through these together. Here, I am also going to just assume that you have all 3 trig identities written down by your side. I'm not going to rewrite them every single time for every question. That would just be a little tedious. So write all 3 trig expressions down right now. Remember, it's sine squared plus cosine squared equals 1. 1 plus cotangent squared equals cosecant squared. And then you should have tangent squared plus 1 equals secant squared. And so for these, all 12, we're going to simplify the following expressions to one of the answers in the box. Answers may be used more than once, or some may not be used. Show a work that leads to your answer. So first we see secant squared theta minus 1. I'm probably going to look more at the Pythagorean identity, rearranging this, so tangent squared theta plus 1 equals secant squared theta. And then I'm going to subtract 1 from both sides to get tangent squared theta equals secant squared theta minus 1. So 1 should be simplified to e tangent squared theta. So e should be the correct answer for number 1. Number 2, sine squared minus 1. Here, I'm going to look at sine squared theta plus cosine squared theta equals 1. And then I'm going to get sine squared minus 1 on the same side. So I'm going to start by subtracting 1 to get sine squared theta plus cosine squared theta minus 1 equals 0. And then I'm going to subtract cosine squared theta from both sides to get sine squared theta minus 1 equals negative cosine squared theta. And that should be our answer. So J there. Number 3, cosecant times tangent minus secant. Cosecant is 1 over sine. Tangent is sine over cosine minus secant, which is just 1 over cosine. Here we can cancel this out. And so we should have 1 over cosine minus 1 over cosine, the same denominator. It's just the same thing minus each other. So this should just be equal to 0. So G should be your answer. You could also just combine like terms as well to get 0 as well. So G should be the answer for number 3 there. All right, so for number 4 here, I see 1 plus tangent squared theta. Using the Pythagorean identity, I know that this is immediately equal to secant squared theta, and then cosine squared theta times secant squared theta. Secant squared theta is 1 over cosine squared theta. These should cancel out, and we're just left with 1. So C should be our answer for number 4. For number 5, cotangent is cosine theta over sine theta, and then secant is 1 over cosine theta. Here, those will cancel out. We're left with 1 over sine theta. That is not any of our answer choices, but I know that is equal to cosecant theta, and so B should be our answer for number 5. Number 6, this is a common misconception. Here, a lot of people, if you see x plus y squared, want to say that this is equal to x squared plus y squared. It's not. You have to FOIL it out. So that's what we need to do for number 6. So here, let's just start, because this will be a tricky one, by simplifying the numerator first. So this is going to be sine theta plus cosine theta times sine theta plus cosine theta. So that's that squared minus 1. Now we need to FOIL this whole thing out. So let's do that. I'll erase that so we can see the fraction. And so sine theta times sine theta is going to be sine squared theta plus sine theta times cosine theta is sine theta times cosine theta. No real way to simplify that. Cosine theta plus sine theta is going to be plus cosine theta sine theta. And then cosine times cosine is cosine squared theta. And then here we have that minus 1 attached to the end. Here we're only focused on the numerator right now. We're really not focused on the denominator yet. Simplifying the numerator, I know this whole thing is the numerator here. I know we can combine sine squared plus cosine squared to give us 1. So sine squared theta plus cosine squared theta that's 1. And then we have this minus 1 here. So this should just be equal to 0. So we can almost like delete all of this from our fraction. So let's do that now, because that will all just sum to 0. And so now we can simplify this numerator to give us sine times cosine plus cosine times sine. We can rearrange the order, right? Let's just write this as sine times cosine. There. And then it's 2 of the same thing. So this is 2 times sine theta times cosine theta. And now let's put it all over our denominator, which is sine theta cosine theta. And here you can cancel those out to just give us 2. So K should be the correct answer for number 6. That would be one where it's like, that's why I'm doing these problems, is for ones like 6. I would say 1 through 5 you should have been able to do on your own. All right, number 7, we have tangent over cotangent minus secant over cosine. So let's take a look here. So tangent, I'm going to rewrite everything in terms of a fraction. So tangent over 1 times 1 over cotangent minus secant over 1 times 1 over cosine. And then putting everything in terms of sine and cosine, here we're going to get tangent is sine over cosine times 1 over cotangent. This is just tangent. That's also sine over cosine. So here we're going to get sine squared theta over cosine squared theta minus secant is 1 over cosine times 1 over cosine. So this is minus 1 over cosine squared theta. Simplifying this, you have sine squared theta minus 1 over cosine squared theta. Using the Pythagorean identities, I'm going to subtract 1 and then also subtract cosine squared like I did before to get sine squared theta minus 1 equals negative cosine squared theta. So negative cosine squared theta over cosine squared theta equals -1. So A should be our correct answer for number 7. I know that took up a little bit of space. We'll separate that from the rest of them. 8 sine theta times cosecant theta. Cosecant theta is 1 over sine theta. Those will cancel out. We're left with 1. So C is our answer for number 8. And then number 9, cosine theta over 1 times 1 over secant theta. This is going to be cosine theta over 1 times cosine theta over 1, because 1 over secant is just cosine. This is going to be cosine squared theta. So that should be L, should be our answer for number 9 there. 10, 1 minus sine times cotangent, which is cosine over sine, times secant, which is 1 over cosine. Here, everything cancels out to just give us 1. So it's 1 minus 1, which is 0. So G should be our answer for number 10 as well. So here we are starting to see a few repeats. That is to be expected. Answers may be used more than once. For 11, we have 1 over sine theta times secant, which is 1 over cosine theta, minus tangent, which is sine theta over cosine theta. Taking a look here, we have 1 over sine theta cosine theta minus sine theta over cosine theta. So to be able to subtract fractions, we want a common denominator. And so to do that, we're going to need this denominator to be cosine times sine. So I'm going to multiply both sides by sine theta to get 1 minus, and then this is sine squared theta over sine theta times cosine theta. Here, this is going to be cosine squared theta from the Pythagorean identities over sine theta cosine theta. Here we can cancel out a cosine from the top and bottom. We're left with cosine theta over sine theta, which is 1 over tangent or just cotangent theta, which is option choice I. So I is going to be our correct answer for number 11. And then number 12, cotangent is cosine over sine times cosine plus sine. So this is cosine squared theta over sine theta plus sine theta over 1. Now to get a common denominator, I'm going to multiply both sides by sine theta as well to get cosine squared theta plus sine squared theta over sine theta. This is just 1 over sine theta, which is going to be cosecant theta, which is option choice B. So B is the correct answer for number 12. That should be all of it from 1 to 12. The rest of these I would expect you to be able to do on your own. Remember, you just have to do the first page front and back for the homework. Day 2 is the rest of that packet as well. If you have any questions, please come see me in office hours, and I will see you guys next class. All right, so here we're picking back up from day 2. Today we're going to be learning about the sum and difference and double angle identities. You would have a Desmos quiz in class, but obviously I'm not going to go over that during the video lesson. All right, so what we've learned in the past is on the unit circle, we've learned how to find sine and cosine of every nice angle in increments of 45 and even 30 degrees or 60 degrees. However, what happens if we want to find sine of, let's say, pi over 12, or an angle that's not nicely on the unit circle? Well, these formulas will help us do that. This is probably one of my lesser favorite lessons, simply just because this will be the only lesson throughout the entire year that you will just need to memorize formulas and apply them to possible equations. But you'll see 1 or 2 of these questions on your quiz as well as on the AP exam. So it is important, but this is the only day of just memorizing formulas, I will say. So the main formulas you need to memorize there's 4 of them. Here, if you have sine of A plus B as two angles, this will be equal to sine of A times cosine of the other plus cosine of the one you didn't find cosine of before, cosine A, times sine of B, right? So that's our first equation. Also, if you have sine of A minus B, this is going to be basically the same thing, sine A cosine B minus cosine A sine B, right? So this basically stays the same. The way we can simplify this is just writing it as one equation, which is sine of A plus or minus B equals sine of A cosine B, and then plus or minus cosine A sine of B, where basically all you need to remember is, let me show you this way. If you are adding these two angles, then you're going to add those two terms together. And if you are subtracting those two angles, you're going to subtract those two terms there. That's the top two equations just simplified into a single one. And so when you see that plus or minus that we see in the formula there, that's kind of where it comes from. Is if you do the top one, you're going to do that top operation. If you subtract the two angles, then you're going to subtract those two terms there, right? Cosine is very similar. If you have cosine, and here it's A plus or minus B equals cosine of one times cosine of the other, so cosine of A times cosine of B, and then the signs are flipped. So if you're adding the two angles, you subtract these two terms of sine of A times sine of B. I'm just going to rewrite it over there, right? So that's going to be our cosine equation. There's a few mnemonic devices to remember some of these. The first one is, remember, sine equals same, cosine equals change. And this is talking about these operation indicators here. Sine is going to be the same on the top and the bottom, right? If you add the two angles, you're adding these two terms. For cosine, so sine is, these are the same there. Cosine, you change them, right? If you're adding the two angles, you're going to be subtracting. So sine equals same, cosine equals change. That's the first way to remember those two equations. The second way is just with a little ditty I came up with. This was something I came up with on my own. I'll only say this a few times, so you will not hear me sing that many times throughout the year. This is one of those rare times. But pretty much the way I remember it is sine, cosine, cosine, sine. That's the way you add two sines. Cosine squared minus sine squared. That's cosine. That's fair. Right? So if you sing it, it kind of sings as like a little ditty. Sine, cosine, cosine, sine. That's the way you add two sines. Cosine squared minus sine squared. That's cosine. That's fair. Is the best way to remember the order of the operations. And then it just goes A, B, A, B, A, B, A, B in terms of the angle measures. So I'll say it one more time. Sine, cosine, cosine, sine, that's the way you add two sines. Cosine squared minus sine squared, that's cosine, that's fair. Right, so that's the second way is the ditty or song, right? Uh, so that should hopefully help you memorize the sum and difference identities. And then we can actually derive the double angle identities from the sum and difference identities. So let me do that now. I will keep these equations on screen, but then I will erase the ones I just wrote because they're the same. And so now let me show you real quick how to derive the sum and, or the double angle from the sum and difference identities. So here, I just erase this. There we go. Perfect. Thank you. All right. So basically, the way that you get this is if you're doing sine of A plus A, where it's the same angle, then it's just sine of 2A, where in this case A is theta. So applying it here, sine of theta plus theta equals sine theta cosine theta plus cosine theta sine theta, which is sine of 2 theta, equals, and then it's this same thing twice, 2 times sine theta cosine theta. That's how you get the double angle identity for sine. For cosine, it's pretty much going to be the same, right? If you have cosine theta plus theta, this is cosine theta minus sine theta, sine theta. Remember, cosine change, so the signs will change there. This will simplify into cosine 2 theta equals cosine squared theta minus sine squared theta, right? So that is our two double angle identities. And now I know what you may be wondering. If you take a look here, we see three different equations. You see that, this, and then that for cosine 2 theta. How the heck did you get the other two, right? We got one. Let's now find 2 and find 3. And so if you take a look at this equation right here, number 1, this is going to be like our central equation, and then you can derive the other two from that equation there. And the way you're going to do that is very simple. It's by using the Pythagorean identity of sine squared plus cosine squared equals 1. So let me do that on this side here. If you have sine squared theta plus cosine squared theta equals 1, if we solve this for sine and cosine, we're going to get sine squared theta equals 1 minus cosine squared theta, or you could solve it for cosine squared and get 1 minus sine squared theta. We're going to take this equation, which is equation number 1, write it twice. So cosine squared minus sine squared. And then for the first one, we're going to substitute sine squared with 1 minus cosine squared. Minus 1 minus cosine squared theta. This just becomes cosine squared theta minus 1 plus cosine squared theta, which is equal to 2 cosine squared theta minus 1. That is our answer, and that's how we get equation number 3 there. Let's do the same with this one, but replace cosine squared with 1 minus sine squared. So this would be 1 minus sine squared theta minus sine squared theta. This simplifies to 1 minus 2 sine squared theta, which is actually equation number 2, and that's how we get our second equation there. Right, so it's just using the Pythagorean identities. I would say I would have these two memorized and write them down on the AP exam on the first section. You'll have a lot of extra time, and then derive the rest of these formulas from it, just in case you need them, but have them ready to go right when you step into the exam there, right? All right, so now that we have derived all those identities, that is out of the way, we can now use those identities to answer questions. So here, using the unit circle, what is sine of pi over 6 plus pi over 4? Plugging that into this equation here, sine of pi over 6 plus pi over 4 should be equal to sine of pi over 6 times cosine pi over 4 plus, remember sine stays the same, cosine pi over 6 times sine pi over 4. Now we need to set these equal to fractions, right? It's only the first quadrant, so it should be pretty easy. Sine of pi over 6 is 1/2. Cosine pi over 4, root 2 over 2. Cosine pi over 6, that's root 3 over 2. And then sine of pi over 4 is root 2 over 2. Multiplying these, you get root 2 over 4. Plus this is root 3 times root 2 is root 6 over 4. And we can just simplify this or leave this as root 2 plus root 6 over 4. That's good enough there. That should be our answer for example 10. Example 11, what is cosine pi over 6 minus pi over 4? Here, using the cosine equation, it's cosine squared, so cosine pi over 6 times cosine pi over 4, minus sine squared, and remember signs change, so it should be plus here, and then sine pi over 6, sine pi over 4 there. Cosine of pi over 6 is root 3 over 2. Cosine pi over 4, root 2 over 2, plus 1/2 times root 2 over 2. Simplifying this, you get root 6 over 4 plus root 2 over 4. Ironic enough, you get the same answer. Root 6 plus root 2 all over 4 there as our answer for example number 11. Here, if we have sine of theta equals 0.7 and cosine theta equals 0.9, these are just actual numerical values. What is sine 2 theta? So let's use the equation. Sine 2 theta equals 2 times cosine theta times sine theta, or you can reverse the order, it doesn't matter. This is going to be 2 times cosine theta, which we now know is 0.9. So let's sub that in now. So 2 times 0.9 times sine of theta, which is 0.7. I'm going to use times there. 2 times 0.9 is 1.8 times 0.7. Using a calculator, you should get 1.26 as your answer there. Right, example 13. These are questions that you're going to see more than likely on the quiz, so just be prepared for questions like these. Which of the following is equivalent to 2 sine pi over 14 cosine pi over 14? Here, this looks like 2 sine theta cosine theta, where theta is pi over 14. And I think to myself, what equation could I use that's pretty similar to that? And that's going to be sine of 2 theta, which is sine of 2 times pi over 14, or sine of pi over 7. So C should be our answer for example number 13. For 14 here, we have 4 times cosine 2x. Which of the following is equivalent? So knowing that cosine of 2x, that 4 is going to stay out front. Let's look at this through all three possible equations. This is 4 times cosine squared x minus sine squared x. Or you could have 4 times 1 minus 2 sine squared x. Or you could have 4 times 2 cosine squared x minus 1. And we want to see which one matches one of the possible answer choices. The first one is distributing this 4 cosine squared x minus 4 sine squared x. That does not match any of our answer choices, so that unfortunately is no good. For the second one, this would be 4 minus 8 sine squared x. That unfortunately is no good. And then this one is 8 cosine squared x minus 4. That is good because it matches answer choice C, which is our correct answer there. So you'll see a question very similar to this on your quiz. All right, number 15. You will also see one like 15 on your quiz as well. Here, which of the following is equivalent to this? So I see cosine, cosine, minus sine, sine. So because I see the same thing, I am going to think of cosine, and then it's going to be A and B, and cosine is changed, so this should be a plus there. And then in this case, A is going to be pi over 8, and B is going to be pi over 16. So you should get that there. So this is what this is going to be equal to. This is equal to that whole expression. And then simplifying this, right, let's get everything in terms of 16. So 2 pi over 16 is the same as pi over 8 plus pi over 16. And now remember how to add these fractions. 2 pi plus pi is just 3 pi over 16. So that should be C should be our correct answer for example 15. You will see something just like this on the quiz, guaranteed. All right, number 16 here. We have a figure centered at the origin with theta in standard position. The coordinates of P are 5, 12. What is the value of sine 2 theta? So this is going to be, let's look at the equation, right? Sine 2 theta is equal to 2 times sine theta times cosine theta. So let's just plug it in. 2, and then sine of theta, right? This should be 13 is our radius, is opposite over hypotenuse. So 12 over 13. And then cosine is adjacent, 5 over hypotenuse 13. So this is going to be 2 times 12 times 5 over 13 times 13. That should be 169. 2 times 5 is 10 times 12 is 120 over 69. That should just be your final answer. You can't simplify that anymore. So that is our answer for example 16. And then 17 here, the figure shows two circles centered with angles A and B. Remember, this is A, and then this is B here. The coordinates are -5, comma, square root 11. So -5 square root 11. And then this is 6 is our radius. And here the coordinates are 2 root 5, and then our radius is 3. Find cosine 2a sine a plus b cosine a minus b. So here, let's draw out our triangles, right? So remember from SOHCAHTOA from 3.2, this is -5, square root 11, and then 6. And then this triangle here should be 2, positive root 5, and then 3. Right, so cosine 2a, using either one of the equations, I'm going to use just one that involves only one trig function. We'll just do the sine. So 1 minus 2 sine squared, and then theta, or a in this case, is going to be our angle measure. Sine of a is equal to opposite over hypotenuse, so square root 11 over 6. And then this is going to be 1 minus 2 square root 11 over 6 squared. So that's 1 minus 2 times 11 over 36, which is 1 minus 11 over 18. And then this is 18 over 18 minus 11 over 18 to give us 7 over 18 as our answer for part A. All right. For part B, we have sine of A plus B. Doing this, we need to find sine of A cosine B plus cosine A sine B. So the first thing I'm probably going to do is just find sine and cosine of each of these angles and label them so that I can just plug them directly into the equation. So here we know sine of A is root 11 over 6. Cosine A is -5 over 6. Here we have sine of B is opposite over hypotenuse, so root 5 over 3. Cosine B is 2/3. So plugging that into B, we are going to get sine of A, which is square root 11 over 6 times cosine B, 2/3, plus cosine A, -5 over 6 times sine of B, root 5 over 3. Here we have a common denominator of 18, so that's good. So you have 2 root 11 over 18, and then this should be minus 5 root 5 over 18. And so I'm just going to leave it as that. You don't need to simplify it. So this should be 2 root 11 minus 5 root 5 over 18. That should just be our answer to part B. There, jeez. Part C, this is going to be cosine of A minus B, which is cosine A cosine B, and then plus sine A sine B. So plugging that in, cosine A is -5/6 times cosine B, 2/3, plus sine A, √11/6, plus sine B, or times sine B, √5/3. Here you have -10 plus √55/18. You can leave it like that, honestly. And that should be our answer for part C. So this is a very tricky question. Very good to get you used to Pythagorean theorem, to get you used to SOHCAHTOA, just as a refresher to that, and then using these formulas as well. You could see this. This is going to be maybe max one multiple choice question on the AP exam, so I wouldn't worry too much about a problem like this. You're going to see something more like 15 or 13 through 15 is like fair game for a quiz. There. All right. If you have any questions, please come see me in office hours, and I will see you guys later. Thanks.